I'm going to talk about the work we've done on blue waters for the past 5 years since we started. We had way back when in the friendly user period. So what's the problem? The problem is supercells produce tornadoes, and tornadoes produce damage and cause death and destruction. Here's a few storms from the last few years, or say a couple decades. 2011, Joplin, Missouri, El Reno, Oklahoma, a couple of tornadoes there. Moore, Oklahoma's been hit a couple times. These are EF5 tornadoes, the strongest tornadoes known to exist. So the problem, looking a little further, is we don't really understand why a very small subset of supercells produce these long path, very damaging tornadoes with surface winds in excess of 200 miles an hour. And I've got winds in excess of 300 miles an hour in my simulation. Crazy strong winds. It's even worse, really, because we really don't understand the processes leading to tornadoes in general. But I will say this work on blue waters has pushed this further ahead. I think we're onto something new and exciting here, looking at tornadoes and why they form and how they're maintained. So the overarching goal of this work is to understand the internal workings of non-tornadic, weakly tornadic, and strongly tornadic supercells well enough to significantly improve our forecasting of their behavior. We want to be able to predict whether a big, strong tornado is going to occur or maybe just a weak one, and alert the public accordingly. This matters because the Weather Service, and I don't mean to rag on the Weather Service, they have an almost impossible task. About 70% of our warnings are false alarm warnings, meaning there is a tornado warning issued and there's no tornado on the ground. There are also cases where something slips under the radar, no pun intended, and a tornado occurs, but it wasn't warned. We had a very weak tornado in Madison a couple of years ago that fell under that category. The large majority of fatalities, however, are these top-end tornadoes. These are tornadoes with winds that are, in excess of 250 to 300 miles an hour. And that's why we're focusing on these particular storms first. And despite advances in both observational meteorology and computational meteorology, we still don't really understand this problem. And blue waters is helping to get much closer to an answer, I think, anyway. So a brief bit of history, since blue waters is sort of winding down. We first started the friendly user period. The initial work we did was focusing on modifying the model we're using to basically the I/O driver to make it much more efficient and also to create a visualization framework. And that stuff was mostly in place when we finally had our first good tornado simulation. So here we are trying different atmospheric soundings to get the storm we want, and it took a while. And after some bumps in the road and ending a PRAC, getting some Illinois money, getting another PRAC, and shuffling things around, we managed to get some very nice data, and I'm going to share some of that with you today. So the storm we focused on was 24 May 2011. This was an EF5 tornado near El Reno, Oklahoma, not to be confused with the 31 May 2013 El Reno, Oklahoma tornado that killed storm chasers that was just over 5 years ago. So El Reno is the place to go if you want to get hammered by a tornado. We have simulated this storm at 3 different resolutions and pretty much gotten very similar results. So we have a pretty good convergence of solution, although there's a lot of initial value issues and Lagrangian turbulence and noise and chaos in these simulations. Rerunning them doesn't always give you exactly the same answer, but we'll talk about that right now. Along the way, in order to manage data, I created a file system and started to use lossy floating point compression. And if those of you who think you need 64 bits of precision, you don't, okay? You just don't. I mean, there are some applications where it might be important, but if you're just going to do post-processing analysis, you can compress your data pretty well with lossy floating point and end up with 20 to 30 times data reduction. I will never go away from this. It's the only way to go for me. But I don't want to talk too much about that. It's a tunable way, ZFP especially, Peter Lindstrom at Lawrence Livermore developed it. You can essentially say, I want this much accuracy for my variable. You cannot have my variable go beyond, say, 0.1 kelvins of accuracy, and it will compress accordingly. Our most impressive data set to date is about 67 terabytes. That's almost a thumb drive, maybe not. 32,400 times every model time step saved to disk. And this is our golden data set that we're going to be analyzing for years, and now it's just a matter of figuring out how to do it without blue waters. In addition to saving data sets with this huge temporal resolution, I've also started to do temporal averaging over time. This has been a really, really good approach to really sort of show the underlying persistent flow features that are responsible for tornado formation and maintenance. And really a new theory is emerging from these simulations. The leading theory of tornado genesis in meteorology is that a downdraft is required in the rear flank of the storm to trigger the tornado. Our work says there's no trigger. You don't need a trigger. You just need an acceleration pedal and slowly pushing the pedal down to the ground until the inevitable happens. And I'll show you that. There's really no distinction between genesis and maintenance in our simulation. Genesis and maintenance are the forces that are causing the tornado and maintaining the tornado are essentially the same. And that is a cleaner theory, I think, than the existing theories. But we haven't quantified this yet. But anyway, to summarize, this really great simulation, many simulations, the spatial resolution, the temporal resolution, the visualizations, this makes it breakthrough work. So great job, Blue Waters. I love this machine. Anyway, so the challenges is first getting the storm we wanted to form. That was really scary. It would suck if you created this awesome environment to look at storms and then you just got boring storms to look at. It was not a foregone conclusion that we were going to get big tornadoes. I was confident we would eventually do it, but it was down to the wire. So that was the biggest challenge, and we're still trying to simulate different environments, and that is proving to be challenging, but we're having some successes in those areas, I think. Managing the data, I've spent a lot of time thinking about this problem, freaking out about this problem, trying to reduce the data to as small amount of data as I can so I can keep it and study it for years. And then there's, of course, the science, making sense of what's going on. Thus far, I have focused primarily on 3D viz to tell a story before we dive in with the quantitative approaches and decide what kind of quantitative approaches you apply to these kinds of big data problems. Some of the accomplishments, these simulations are having an impact on the severe storms community. People are now looking for things we've seen in the model. That's very gratifying for me as a modeling guy. There's been field programs are being conducted that are involving looking for some of these things. There's been a lot of PR. There's a Cadence documentary. The American Museum of Natural History is doing something. I sent them a 7 terabyte hard drive and said, have fun. So they're going to do something at their museum. Several journal articles. We've got grad students who have and are working on the data. And various venues on YouTube, about 500,000 views, which is pretty impressive. So lots of broader impacts. So here is a picture about 10 to 15 minutes before the tornado forms, showing the vorticity magnitude shaded by, in this case, the updraft velocity or speed, and then the absolute magnitude of the wind speed. Two different ways of looking at the same thing. But what I want to focus your eyes on are these tubes of vortex tubes. Okay, the general understanding in meteorology is you cannot tilt near ground horizontal vorticity into the vertical to produce a tornado. There's not enough of it. As you approach the ground, the vertical vorticity goes to 0, so you can't stretch it. Well, what I'm here to say is, if you look into the cold pool and realize that the air that is filling the tornado is actually coming from the cold side, it changes the context of things a little bit, because now you're sucking air up from a rather turbulent cold pool which is just drowning in horizontal vorticity, but there's enough turbulence and noise that there's going to be some vertical vorticity, so you can stretch the heck out of that if you can get a strong enough updraft to do it. It's all about the updrafts. So this is an animation in every single model time step. You can't see any more than this. The SVC, the streamlined vorticity current, is highlighted. I mean, look at this. Tell me that the updraft is not tilting that. I mean, it's like an L. It's a backwards L. So that's one of the big results here. What's causing this? Well, it turns out there's a very strong updraft, and I've painted, I don't have the scale here, but this is like 60 meters per second as you get into the green, or thereabouts. The updraft is so strong, it's just sucking up vorticity from all quadrants, and there's your tornado. There was no trigger in the formation of this vortex. It was just basically a steady amplification of a strengthening updraft until it manages to coalesce all the vorticity into one spot, and then the tornado sort of forms. And another animation will show this even better. The vorticity that leads to the tornado, you'll see that there's a parade of vortices that kind of goes by, and then it sort of slows down, and then it just kind of accumulates, and then you get your tornado. So this is sort of our emerging model of tornado genesis. Here's another view looking from the other direction. So here's our streamwise vorticity current right here. You'll notice, so we're looking at it from the cold side, so we're looking west. So some of this vorticity here is horizontal. You can see that they're organized into tubes and that they are being tilted upwards. And you'll see right about now this great convergence of all these little vortices. This is where the updraft is getting super strong at low levels. And vorticity in these little vortices is consolidating to basically one main vortex. But the real story is what's going on aloft with this strengthening updraft. And I'll show you an animation of the pressure field that I'm really interested in, because it's really kind of stunning how fast the pressure drops, like 1 to 2 kilometers above the ground, and how that results in a very strong non-hydrostatic vertical pressure gradient that helps to cause some of this vorticity stretching that leads to the tornado. But it's not just about stretching vorticity, it's also about vorticity, a budget. You have to get the vorticity from somewhere else. You don't create it out of nothing. So this animation here is before the tornado forms. The blue guys are anticyclonic vortices, the red guys are cyclonic. I guess I'll pause it right here just to sort of make sure we're not all on the same page. This is the forward flank of the storm. This is kind of where the storm is going. The model domain is moving with the storm. In fact, that's a key to the success of this work, is that I've basically got the storm motion vector locked in so that it's always in the center of a domain. That's how I can do the temporal averaging. So this is the forward flank. You'll notice these vortices, the red, red, blue, red, blue, red, blue. They all, at this stage in the game, they're these tall, skinny vortices, and they're moving towards the rear of the storm. So we'll let this go. This is in 1 second intervals. This is your SVC sort of forming, and this is that horizontal vorticity being tilted. Now look at all of a sudden, these vortices sort of, we're going to stop moving rearward, and actually there's a sweep around, and right when you start to see it sort of reverse, boom, tornado. I'm thinking of calling my new theory boom tornado, because I always say that. But anyway, so this red guy, this very strong cyclonic vorticity, and all these little blue guys, you'll see some of the blue guys, the anticyclonic or clockwise rotating vortices, get kind of messed by the big one. Now watch how these blue guys almost grow out of the ground. This is the thing that, yeah, there's a strong updraft here, and yes, you are stretching vorticity, and yes, you are tilting vorticity with a very strong updraft, and watch how this blue guy just kind of grows out of the ground and then kind of fights with the main vortex. It's very interesting what's going on here. But then things just get locked in, and it just goes and goes. You start to see it, the two-celled tornado where you have a downdraft in the center and twin intertwined vortices. That's been shown in chamber models. But it just goes and goes, and eventually some of the rear flank, there's energy, or at least lots of anticyclonic vorticity being kicked out from the rear flank of the storm. The rear flank of the storm does not appear to have any important role in this simulation. And again, the leading theory of tornado genesis is that the rear flank has everything to do with the tornado. So that's what makes this work, I think, significant. It really suggests that there's another mechanism going on, at least in this storm. I'm only going to claim for this storm, but we're going to start looking at new ones. And you can see how eventually the tornado gets sort of occluded. It gets, it's fighting with a lot of junk coming around from the rear flank, but it manages to persist for quite a while. And eventually I have to stop this because we'll be here all day. Because I made all this on Blue Waters. So that's pretty cool. All right, so this is the new stuff that I've just started to look at. These are temporally averaged fields over a 2-minute time period. So each of these fields contains 121 times averaged together. I'm using a moving window centered average in 1 second intervals, and I'm going forward and doing that. This, for the pressure field especially, if you look at the pressure field in atmospheric models, lots of wobbling around, lots of wave action. All right, now these are isosurfaces, okay? Updraft, pressure perturbation, and just watch what happens. Pressure is dropping. Updraft is starting to lower to the ground. Pressure is dropping more. Now you're at 20 millibars. This is where our SVC is. The updraft is going further and further. The stretching term in the vorticity equation has to do with the vertical gradient of the updraft, and it is really strong. And eventually, boom, tornado. I mean, no trigger, there it is. And you can see the signature of the SVC here in this little lobe of low pressure. We believe, and we haven't quantified this yet, that it's the SVC that's leading to this intense updraft lowering to the ground due to that vertical pressure gradient. That in turn is increasing the stretching and the convergence beneath it to cause the tornado and to maintain the tornado. Okay? Tornado genesis and maintenance are the same thing in this simulation. And it goes on and on. Updraft velocities of, speeds of 50 meters per second, 500 meters above the ground. Maybe that's like, 100 and something miles an hour. And updrafts within the tornado itself can be ridiculously strong because the vortex isn't perfectly vertical. So you get easily, 60, 70, 80 meter per second updrafts in the tornado. That's probably how you loft cows and cars around, partly, is because you have a really strong updraft near the ground. There's also aerodynamic effects, to be sure. But this approach of temporally averaging the data that's been saved at very high temporal frequency has taken away a lot of the noise. You lose sight of the forest for the trees, really. And this takes the trees out and leaves the forest, in a sense of speaking. So yeah, updrafts near the ground in tornadic supercells are wicked strong. At least that's what this shows. And you know, the rear flank, not much going on there. By the way, this blue surface is the cold pool temperature deficit. So gradients in temperature in the cold pool lead to baroclinic generation of horizontal vorticity. That gets the vorticity going like this. And that's probably the source of most vorticity. But then the updraft consolidates that. It stretches it, it tilts it, and basically concentrates it into the tornado. That's what it looks like. One of the big results of this work is that the tornado and much of the lower level mesocyclone is entirely comprised, or mostly comprised, of cold pool air. And here you are with these vortex tubes. I mean, if this isn't vortex tilting, I don't know what it is. It's basically, the updraft is peeling vorticity nearly from off the ground and tilting it upwards and feeding it into the mesocyclone circulation, helping to maybe, you know, lower the pressure to maintain this strong tornado. So there's different moving parts in here that I don't think have been seen clearly in field data or previous numerical simulations. But yeah, these movies just tell such an intriguing story. But it also tells a pretty clear story. This is updrafts. Updraft is lifting those vortices, stretching them, converting that horizontal vorticity into vertical vorticity. And there is definitely you know, quantitative budget analyses we need to do to make sure that I'm not wrong here, but the pictures tell a real story. And yeah, these twin vortices have been seen in chamber models. So, all right, one of the big things in meteorology is, especially if you're a modeler, is okay, it's in the model, but is it in the atmosphere? You know, you get that a lot when you're a modeler. Well, this little sequence here was developed in collaboration with a professional videographer and storm chaser named Hank Scheima. He went to his extensive catalog of video and photography to compare some of my renderings to what he's seen in the field. David Bach at NCSA made this wonderful visualization of my data, and now we sort of put it side by side with, say, towering cumulus clouds in a real storm. So this is obviously you can tell this is simulated and this is real. In some cases, it's not always clear which is which. Mammatus clouds, you'd be forgiven to think if that is real, but this is real and this is actually the simulated data. I did a little color shading to make it slightly more similar. The tail cloud is a region we're focusing on extensively because this is where it's right, sort of delineates where the SVC is. It's behind the tail cloud, so that's kind of where we're focusing. And this one I really love. This is the SVC again, and look at the clouds here. I mean, this really shows a similar regime in the atmosphere compared to the simulated data. Here's a sort of a stovepipe tornado, or I don't know the different nomenclature, but looks pretty good, the same aspect ratio. Here's the tornado at later phase. It looks similar to this guy here. This was filmed sort of serendipitously by a guy who got stuck on I-39 near Rochelle. Notice the multiple vortices, okay? Multiple vortices showing up very clearly, looking very similar to field data, or field data of opportunity, shall we say. So I think we're on the right track. These subtornadic vortices, the smaller ones, we're capturing, or at least we're resolving them, and you see those in real data. This is the Katy tornado a couple of years ago in eastern Oklahoma. And there you have it. So it's pretty good. Parting thoughts, sort of to close things out. You know, to be clear, Blue Waters has enabled some breakthrough science in atmospheric science with supercells. This is a real leap forward, I think. The tremendous amount of data will be analyzed for years. It's going to go beyond Blue Waters, which is a source of anxiety a little bit, but you know what? We'll figure it out. If all else fails, I'll rerun some of these guides if I have to. But I think with the data compression and the file system I've created, we're going to be able to squirrel away a lot of this data and still do some science. I'm really looking into accelerators, primarily GPUs. They're getting cheaper. You can buy an NVIDIA card and slam it in your machine and hopefully do some nice things. We'll see. I need to learn. The portability of the file system and underlying data format is HDF5, by the way. It enables us to move the data to other machines and do more post-processing, which I think we will be doing. And with that, I'd like to acknowledge my collaborators, Catherine Finley, she's co-PI on the PRAC, Bruce Leigh, Rob Wilhelmsen, who started the ball rolling many years ago and also started the first PRAC that we got. He's one of the world-leading cloud modelers from the 70s and 80s. And my graduate students and, of course, NSF and the Blue Waters team.